So what is local linearity anyway? Well, we've already said that a function can have a tangent line at a specific point if the tangent line matches both the y value of the function and the slope of the function at that point of tangency. So if that happens, if there is a tangent line at a point, then we say the function f is differentiable at that point, and the point is a f of a. So we have to have a defined slope there, which means we have to be able to draw a tangent line that is not vertical, because a vertical tangent line does not have a defined slope. So we use the notation f prime of a, or f prime at a, to represent the slope of the function x at the point x equals a. The function f at the point x equals a. So we should have a unique tangent line to the function at a particular point. If there's not a unique tangent line, then we do not have a slope that we can define at that point. That's like the absolute value function with that sharp corner. No unique tangent line can be drawn at that point. Therefore, the absolute value function would not be said to be differentiable at that point. So the concept of local linearity is this. If you zoom in on a function again and again and again and again, using your TI calculator, using Desmos, you actually find the function will appear linear. So what that means is on a very small neighborhood, and we're talking microscopically small, like we've zoomed in again and again and again, then you could not even distinguish the function from its tangent line. This is the concept of local linearity. And in fact, you've seen this equation already. You've seen actually something similar to it. You saw y equals f prime of a times x minus a plus f of a. The y equals meant that it was the equation of a tangent line, but the tangent line was best approximating the behavior of the graph at that point. Y equals the equation of the tangent line. F of x is approximated by the equation of its tangent line. So what we're saying is that if we have a tangent line to an equation, it will approximate the behavior of the function, and that's why we can say f of x is approximately equal to its tangent line in a very small area. So we refer to this expression as the local linearization. Now I warn you that when you are writing a tangent line equation, you may not write f of x equals, because f of x equals is not correct. Y equals is correct. You've got a tangent line equation. F of x is approximated by. You would have to use the squiggly approximations for that. So let's take a look at an example. So we're going to consider the radical function f of x equals the square root of x. The slope of this function at any point on the domain is given by this expression, and we're going to pretend that you don't know the power rule, even though many of you do. So you don't know how we got that. You're just taking us at our word right now. So then we say, find the slope of the function f of x equals the square root of x at x equals 4. Well, we just take 4 and we're going to plug it into the tangent line expression, and we're going to get out 1/4. So we will say that that is f prime at 4. So if I want to then write the expression for the local linearization, remember that local linearization is really the same thing as the tangent line. So if you were ever asked to write the equation or the local linearization, you're just being asked to write the tangent line equation of a function at a given point. So my tangent line is going to be y equals 1/4, which is the slope, and then x minus the x value of the point of tangency. And then to get the y value of the point of tangency, we plug 4 into the absolute value expression and we get out 2. So this is our local linearization of the function y equals the square root of x at the point 4, 2. The next question asks if we could use the example or the answer right here to approximate the value of the square root of 4.1 without using a calculator. In order to do that, what we're actually going to do is take our local linearization or the tangent line equation, and we are going to substitute in the value for x of 4.1. And this kind of confuses people sometimes when they first see it, but all we are doing is saying that the square root of x is being approximated by this linear equation near x equals 4. So we're going to use this input value here of 4.1 into the function the square root of x. Okay, the input value goes in as our x value. So we're going to have 4.1 minus 4, which is 0.1. 0.1 times 1/4, which is 0.25, is 0.025. So our local linear approximation for the square root of 4.1 is 2.025. So going on to the last page of this lesson, they're asking us to go ahead and graph the square root of x on the grid that's given. So we'll just do that by plotting a few points. Square root of 0 is 0, square root of 1 is 1, square root of 4 is 2, and here I can graph my square root function. And then they want us to also graph the tangent line equation. So I'm going to graph the tangent line here. Let me see if I can pull out a linear tool. So here we go. There's approximately my tangent line. Now, based on what we've just drawn, do you think that my answer to question 3, which remember we used the local linearization to approximate the value of the square root of 4.1, we said it would be approximately 2.025. So do you think that 2.025 is too big or too small? Does it overestimate or underestimate the actual value of the square root of 4.1? And you need to justify your answer with respect to the behavior of the square root function. Well, looking up here, I see that my tangent line looks like it is above the function, which means that a y value, say right here on the tangent line, will be above the y value right there on the function. So I'm going to say that my tangent line is an overestimate, and as far as the behavior of the graph, it is because f of x is concave down. So we're tying together what we learned earlier in this lesson, where it appears that concave down curves have a tangent line that lies above the graph. Now, if you go into your calculator and you find the exact value for the square root of 4.1, you're going to get approximately 2.0248, which is very, very close to 2.025, but it is lower than it, which is exactly what we thought. We thought that 2.025 would provide an overestimate, but the error in my estimate is only 0.0002. It is very, very small, which is impressive that we just used a linear equation to approximate a value close by on the graph. Why couldn't we use the approximation that we had for the function at x equals 4, which, if you recall, was 1/4 times x minus 4 plus 2? Why couldn't we use that to approximate the value of the function where x equals 16? Well, let's try it. If I plug 16 in for my x value, I'm going to get 1/4 times 16 minus 4, which is 12, plus 2, and then 1/4 times 12 is 3, plus 2 is 5. So we are estimating that the square root of 16 is 5. That is very far off in terms of calculus speak. You know, a difference of 0.0002 is very small, but a difference of a full digit is very large. The reason why that this does not work is 16 is too far away from my intersection point of the point 4, 2. So when I say local linearization, what I mean is that we can use our tangent line equation to approximate a point very close to the point of tangency in its locality, but not very far away, as in 16 compared to 4.